The bulk of this is actually what we already know from CS24, but what we're going to talk a little bit about is just the historical aspect where some of these things came from, some of the techniques that other systems have used. So maybe if I do anything, I'll try to blow through this stuff that we're already familiar with, and then we can spend a little bit more time talking about the interesting variations. But, we have programs writing and reading memory. That's not a big surprise. And, of course, the source code doesn't have addresses most of the time unless you're writing a PC booter or something crazy like that. Typically, we just use symbols, and then what happens during compilation and linking is that addresses are assigned to these things. So functions and variables, we refer to them by name, and then we replace those things. And then there's another aspect of the picture, which is that the operating system has to figure out how to load and run programs. And so typically, we have this thing called the ABI. You've probably heard of the ABI. If it's only been in this class and a lot in this class, then I feel really sad because it's typically, if you know about the ABI, it's because it's painful. But the ABI is basically how to lay out the program so the operating system can load it and start running it successfully. And so this would be things like your stack starts at this location and grows down. Your binary code should start here and it goes up, and typically it should expect anywhere from 0 to 3 arguments, and there are these things, and return an int, and blah, blah, blah. So those are all part of the ABI that's specified by the operating system. Now we can have different kinds of code. We can have absolute code where we have addresses encoded in the instructions, so you can certainly do that. You can also have relocatable code, which is generally what we generate nowadays. Back in DOS days and on the PC at least, you would have absolute code. It would always start at 100 hex because guess what was below 100 hex? It was the interrupt vector table, which you could write to. It was really fun. And, then it got really wild after that. So anyway, relocatable code is the typical way of doing things because most of the time we can't guarantee that all of our stuff is going to be loaded exactly where we expect it to be. And so object files will actually say, these are the parts of my program that refer to things that might vary where they're located. So it can go through and patch those things at load time. So there's a little bit of linking that happens right at runtime. Okay, yeah, blah, blah, blah. So I already talked about that. And then you have the most interesting stuff, which is position-independent code, which is not too difficult to do on most operating systems. Like OS X is like almost all position-independent code because of the way that they basically require everything to be shared libraries. They don't really support static linking unless you built the library yourself as an object file and can just link it in. So position-independent code typically not a big deal on IA32. The only parts that are challenging is when you want to access global stuff at a specific address. Then you need to find your own address. So typically you see calls like call the next instruction and then pop whatever was on the top of the stack into a register. That's how you read EIP, so you can figure out where you're actually located. Things like that. Fun code. So ELF supports all of these things, and on Linux, of course, this is stuff that we're already familiar with. You have executable object files where the .text segment starts at 804.8000. Then you have relocatable object files, which we generate all the time. Those are our .o files. Typically, .text starts at 0 and goes up, and .data starts at 0 and goes up, and .ro data starts at 0 and goes up. And we need to relocate things so that it will actually be usable. Shared libraries will be compiled with position-independent code. And then there's Windows Portable Executable, or PE files as well. So these are your .exe files. And they have the same kind of thing. They support all of these same ideas. Okay? And at some point in the future, when we actually start supporting UEFI, which I've been researching a lot, I think I've mentioned that before. Did I mention this already, that UEFI actually requires a portable executable format binary to run? So if you want to write a UEFI OS loader or a UEFI application to run in the pre-boot environment, you actually have to build it and link it using the Windows portable executable format, which is great on Linux, right? You have to now support cross-compiling and cross-linking just to support UEFI. Hooray. Well, I guess that's because Microsoft helped create this with Intel for the Itanium processor. That's kind of the reason why we have this stuff in the first place. Okay, enough of this. Yeah, so portable executables, you can rebase them. That just means they have a preferred address they'd like to be loaded at, and you can relocate it if necessary. So that's the idea behind portable executables. Okay, so we have programs emitting addresses to the processor, and the processor then needs to take those and access memory on the program's behalf. And so these are virtual addresses because we can, we typically do translate them into physical addresses. And this mapping mechanism, of course, uses the memory management unit. We talk a lot about how that works in CS24. Now, of course, we're drawing this as a blank box because a lot of times the MMU historically would do a lot of other things besides what we talk about it doing recently. So we'll talk about things like segmentation and relocation, and there's like probably 3 or 4 different ways that page tables are structured and managed, and it gets pretty wild. So we'll talk a little bit about that in a moment, but the first question, the obvious one, is why do we want virtual memory in the first place? It adds a lot of complexity. You're probably going to hate virtual memory starting in a few days when the virtual memory project starts, and the assignment says write a virtual memory system in this directory, and you go and it's empty and you cry. So that's a great way to start any assignment, is to cry. So the big obvious reason why we like virtual memory is because of process address space isolation. We need to have some barrier between executing processes, and we want to make sure that that barrier is absolutely insurmountable, which means implemented and enforced in hardware, unless processes specifically agree that we want to communicate with each other. And typically, both sides have to actually agree before that collaboration will be allowed. And so separating address spaces is a great way to isolate processes. You can basically make it impossible for processes to access each other's data. Okay? And of course, the way that you do this is they even can refer to the same virtual addresses, which we'll talk about in a second, but you map them to completely different regions of physical memory, and then it's not possible for processes to change this mapping or to access each other's physical memory. Okay, so that's the first benefit. The second benefit is related to that, because if we can have this virtual address space mapped to physical memory however we want, then it makes the ABI really easy to specify. Yeah? How does the memory work right now between 2 processes? So in the user process lab, you actually have page tables. So in process.c, if you look through there, and if you're wondering why I've been being quiet on Piazza, it's because a lot of that stuff a lot of the questions you can figure out by just looking at process.c. There's a little section which you'll have to change in Project 5. You get to increase the number of page faults occurring. Basically, I think it's like load and then load segment and stuff. Basically, it walks through the ELF header and adds pages to the address space for each process, and it also updates the page table for that process. And right now, you have to get a page, right? Yeah. Well, if you're making the stack, you do, because if you're, just for loading, I think the code is already in there to load the page data for the pages that are actually from the executable file. Like the binary file is already loaded for you. So the data is still separate. What do you mean is, between 2 programs, yes. So there's like, what is it? There's, I can't even remember all the function calls, but there's like pal alloc page or something. And yeah, it'll allocate separate physical pages, and then it will map them into the virtual address space using the page table. And so every process has its own page table, and when you context switch to a process, you change the page table base register to point to the new process's page table. And the only reason you're allowed to do that switch is because all the processes have the kernel mapped in the exact same location. So when you're in page table 1, the kernel's at this spot, and then you switch to page table 2, and the kernel's still at the same spot. So you can do that switch, and the kernel is able to keep executing. Yeah. So that is virtual memory, and that is isolation. So we don't have to implement isolation in PINTOS. But what you will have to implement in Project 5 is basically demand paging. So now we can actually overcommit, and this is what we're going to talk about as our third point here, is that we can actually overcommit physical memory, and the operating system will page out pages that are unused or whatever policy you decide to choose. You can page out some of the pages that are in physical memory and store them on a swap device. And then you can load them in when you get a page fault for that page. So that's the idea of what you'll implement in Project 5. So isolation exists already, but what Project 5 will require you doing is implementing demand paging. Yeah. And it's going to be interesting because your stack grows, and how do you know you need to allocate a new page for the stack? Well, because you get a page fault below the current top of stack. You're like, oh, okay. Or actually, I guess the ESP will be subtracted from. So you'll have to figure out all that kind of fun stuff. When do you say the program has a bug, and when do you say they need a new stack page? So you have to come up with a heuristic. And I think the assignment suggests some heuristics you can use to make sure that that works correctly. So, yeah. Does that answer your question? Were there any other questions related to that? This is potentially as important as what I have to talk about. So, because this will obviously affect your quality of life for the next 2 weeks. So anyway, yeah, so the ABI design is obvious here that if you basically can isolate people's physical address spaces and give them the same virtual address space, then we can lay them all out the same, and that makes our operating system implementation a little bit easier. So this is the 32-bit Linux process layout. I just got the new third edition of the CS24 Computer Systems book, and it says the 64-bit layout, which is pretty straightforward as well. It actually starts a lot lower, and you get a gymongous address space for the user process, and the stack always starts like right below kernel space and grows downward. Okay? So this is an example of how all processes basically follow the same pattern. Okay? Those are two reasons, so isolation and simple ABI. The third reason is that we can overcommit our memory. Why do we want to overcommit memory? Any kind of overcommitting sounds like a terrible idea, especially if I have like too much debt, then that's an overcommitting on my part, and I'm sad. But in this case, we actually like it because there's a lot of situations where programs aren't able to run, and they may in fact not be able to run for a really long time. And so if the process is unable to run, why require the physical memory commitment of that process? Why don't I move some of that memory out to a backing store so that I can free up physical memory for other processes that are able to run? So this is a really common thing. And you might say, well, it seems really crazy to swap stuff out, but think about a giant program like Microsoft Word, or pick your favorite giant program, and I might be spending most of my time in a small chunk of that program's code. So there's no reason to have the rest of that program's code loaded in physical memory. I should leave it on the disk and then pull it in as it's needed. So we call that demand paging. We're not really talking about demand paging today. We'll start talking about that probably next time. But we're just starting to introduce some of the basic concepts. So you have swapping, where I can move a process out of physical memory onto a backing store, and then I can swap it back and move it back into memory. Now you'll notice this is kind of a funny thing. When the scheduler switches to a new process, the dispatcher checks to see if the process is in memory. Well, guess what? If it's not in memory, guess what I just decided to do? Wait for like 30 million clocks, or maybe wait for a few 100,000 clocks if I have a solid-state drive or something like that. So clearly you can have a process that becomes ready to run and then immediately blocks again because it needs to wait on the swap device, something like that. Why would this be a situation? Well, imagine that I have a text editor open on my computer. I haven't written anything in it in a few days, and then I go click on it because I'm like, oh yeah, I need to write Aunt Gertrude or whatever. And so I click on it, and now I want to bring it up, but now it's got to all be pulled off the disk because it's been swapped out for a really long time. Or you might have a situation where you send a process a signal, and it goes from being blocked or suspended to ready to run, but all of its data has been paged out. So now it needs to be loaded into memory. So you can sometimes have these situations that can occur. Okay, yeah, so this is what I was talking about before. Swapping does add a significant cost to the system. It slows down a particular process that's swapped out because it's got to be brought back in. So this is one of those things where you need to sort of achieve the right balance. I want to try to swap enough that I get a huge benefit from overcommitting physical memory, but I don't want to swap so much that I actually slow down the entire system. And it's great because I've actually had a few of you talk to me and say, you know what, my computer slowed down a whole lot because of swapping. And now you actually understand what is going on under the hood. So that's kind of a neat thing. I remember when I was in high school and computers were a lot lamer and weaker back then, and disks were slow, and you would easily tell because the disk light would turn on and your computer would slow to a crawl. Okay, it's thrashing now because it's just spending all its time swapping and none of its time computing. Okay, standard swapping. We don't do this anymore, but we talk about standard swapping because some of the older memory management techniques required standard swapping. Basically, you're moving an entire process out of memory onto the swap device, and then you're moving the entire process back in. So this is slow, and so OSs don't really do this anymore. You don't get any of the benefits that I talked about. You have your 1 gig program. Why do I have the whole 1 gig program data in memory? Why not just swap in the parts that I'm using and swap the rest of it out? So most OSs, modern OSs, focus on swapping just pieces of programs in and out. And that allows you to have a huge performance benefit. Now, mobile processors, everybody with a cell phone, if you've got an iPhone or you've got an Android phone, then you've got a device that is able to do swapping as well. And so even though we don't really have a giant backing store, because typically we just have flash memory that we can use for more persistent storage, but we don't have a hard disk or something like that. So they don't implement swapping in the same way, but they still like virtual memory because it allows you to have address space isolation and it allows you to have a simple ABI. What the OS does is when some part of the system needs more memory, the OS goes and asks everybody, or if it's iOS, it tells everybody, hey, you need to give up some memory. And if the process is unable to relinquish memory the way the OS would like, then the OS frequently just kills the process. Okay? Which is pretty funny. I don't know if any of you, I have it happen like at least once a week where I'll be doing crap on my phone and then all of a sudden the app will just shut down. You may have had this experience as well. A lot of times this is because the OS decided your app is using too much memory. I can't keep running it. So guess what? Bad user experience day. Boom, it shuts down. Okay? So not a big deal. People just restart their apps or whatever. But this is the kind of thing that's going on under the hood. Android is nice in that it will actually try to persist critical data for an app to flash memory so that it's easier to restart. So we can just pull it from flash memory back into DRAM or whatever, and then it can go ahead and restart that app where it was or close to where it was without too much difficulty. So Android tries to do a little bit more, I think, in this area than iOS, although iOS may have improved since I wrote this slide. So kind of an interesting thing, though. You still see paging and swapping factoring prominently on mobile devices, even though we don't have a backing store. Okay, let's see. So any questions? Obviously, this is very general stuff right now. So first, simplest technique that you can use for actually managing process virtual memory is to have some very simple relocation mechanism. Notice how simple this is. We have a relocation register with some value, and we just add that value to virtual addresses, and out pops the physical address. That's all we do. We just add some relocation amount to the virtual address. Now you can also apply a limit. So now you have two pieces of configuration for processes, each process. So this is like the most simple version of a page table. We have a relocation register and a limit register. The limit says this is how much memory this process gets. The relocation register says this is where in physical memory the process's address space starts. And of course those two things are protected, so only the kernel is allowed to change a process's relocation and limit registers. And what that allows you to do is to lay out processes contiguously in physical memory. Okay? So you compile your program starting at some specific address, 0 for example, and when the OS wants to run it, it just sets up that process in physical memory somewhere, says this is the relocation and limit register values for this process, and that basically allows the processor to map addresses to the appropriate region of physical memory. Nice and simple. You get isolation, but you don't get much else. This is a pretty crummy way of doing things. Like it says here, this is basically contiguous memory allocation. That's the name that we give to this thing. And what if you want to swap out just a part of a process? We don't really have a way of doing that. We have a very simple mechanism. Limit and relocation value. That's all we have. What if we have processes that are starting, and so they use a certain amount of memory, and then they terminate, and now we have a hole in our memory, and some other process needs a chunk of memory to start running. You can see that this kind of approach can suffer from fragmentation over time. Remember, fragmentation is caused by differing size allocations that have different lifetimes that become intermingled. Okay? This is what generates fragmentation. And so you can see that if we have this kind of situation where we have processes requiring different amounts of memory, and they I shouldn't say allocate, but they are assigned a region of memory, and then they terminate, and now we have an available region of memory. Over time, we can have serious fragmentation issues. Okay, and all of the same things that we do in CS24 to deal with this kind of stuff, we would have to use here. So you can see this is a very limited approach. Okay, standard swapping, that's another thing that kind of sucks about this, is that you can't page out a part of a process. You kind of have to swap out the entire thing and then swap in the entire thing. The other issue, can we actually share memory using our simple mechanism? Only if we're crazy, right? Because we could have two regions of, two programs that are overlapping. One's end overlaps the start of the next one. That sounds terrible. Okay? And if we did something like that, then you can imagine now we have to worry about our ABI. How in the world do we actually share memory with this simple mechanism? So you can imagine that this was not used for very long. Segmentation is basically a more sophisticated version of this, where we have multiple segments, each with a starting address and a size. This is actually what IA32 or x86 has provided. I should be very careful because it really is from the 386 onward that you would say that they've provided this nice segmented memory model. So you have a segment number plus an offset within the segment. So you can imagine our CS, DS, ES, FS, GS, SS. So we have 6 segment registers that we could use. You have a segment selector in there, which is an index into some segment table that describes that memory segment. And we can do the same thing we had before. We have a starting address or a relocation value and a size limit as well. And so now the segment selector is used to look up the base and the limit, and if the access is beyond the limit, then we page fault. Otherwise, we go ahead and add the base to it, and out pops the physical address. That's basically all we do. Okay? And this is a much more appealing approach than the simple relocation model. And yeah, so this is also obvious. Each process has its own segment table describing the segments that it needs. Because it turns out that programs generally have different regions of memory with different characteristics. And so this model works really well for programs. This is why even the really advanced Core i7 processor still has this memory model. It still provides it as an option. Okay, so we have read-only versus read-write. I have executable code. I have something that should not be executed, and so forth. And you can configure those things in the segment table, and then the MMU can enforce those things. Okay? I mean, it's pretty wild when you look at page faults. I don't know how many of you have actually done the deep dive into all the page fault details, or if you're just sort of steering clear of that right now. But if you have a little bit of time in Project 5, spend a little bit of time reading about page faults in the information that comes back. You can find out if it's an instruction access. You can find out if it's a data access. You can find out if it's a read or a write into a read-only segment. You can find out all these things that the processor will tell you. And so you can imagine that gives you a lot of capability to implement very interesting abstractions in your operating system. And the processor will enforce a lot of things for you. So these are some examples of kinds of data: program text, obvious; constants, read-only data, also obvious; global variables, memory heap. Global variables are interesting because remember, we can have uninitialized variables, we can have initialized variables. Okay? We can support those two things separately, so that's why we have .data and .bss in programs. Memory heap, program stack, which is fun, and shared library. So things like that. So it's easy to come up with at least 6 segments for programs. So now program data does not have to be contiguous. Now each segment still has to be contiguous. I still have to have a single contiguous chunk. So that's kind of annoying when it comes to swapping, but at least now these segments can be interleaved, so I can actually have a reduced fragmentation issue over time, because I have more little pieces that I can fit into various places. Okay. It turns out that this is also really easy to do for shared memory, because maybe you have your FS or your GS, you say, okay, this is going to be shared memory region with another program, and you can go ahead and use that. That's pretty easy. But swapping still sucks, especially if I have a giant heap, so my data segment is humongous, and I can't page out little bits of it because I don't have support for that. I only have segmentation. Now, both of these I mentioned have issues with fragmentation. That turns out to be pretty easy to fix. I also mentioned external fragmentation and internal fragmentation a few times, and since we skipped the kernel allocator lectures because my throat was just very upset. Just to remind you, external fragmentation is, man, I can't remember this. External fragmentation is due to program behavior, and internal fragmentation is due to the allocator's behavior. So it's basically allocators can't avoid it, and the external fragmentation is basically the programs can't avoid it because it's the allocator's characteristic. I think I got that right. We'll see. Anyway, so but the thing is that these models can support compaction. So that's really nice. I go into the kernel, I trap into the kernel because I'm terminating. What the kernel can do now is actually relocate processes in memory and compact free regions. So that's nice, but moving programs is slow. And so you can imagine this actually can impose a significant time delay. But it does allow you to sort of re-compact, re-smush your memory around so that you have more space for running programs. So that's pretty nice. Yeah, if you have a time when system load is light, then you can go ahead and do that. Otherwise, you may have to do it, and so you just do it when everybody needs it done. So you can have these kinds of situations. All right, so that mitigates the fragmentation issue to some extent. Okay, paging. So paging is the one that we're all familiar with because this is what mostly everybody does, but now you know that there's other ways of doing it. Basically, you divide memory into fixed size blocks. So IA32 seems to really like 4 kilobyte blocks. Now you have large blocks as well. I know that IA32 can do 4 megabyte blocks, and I can't remember what x86-64 can do, but it's got a number of larger block sizes as well. And so these are called frames, just like picture frames on a wall. This is the the physical memory that I have to hold program memory. And the virtual memory blocks are called pages. And anytime I have a memory access, I take the virtual address. These pages and frames are all powers of 2. So I have a certain part of that address which is an offset. That goes straight across. And the virtual page number is somehow mapped to a physical page number. Now I say mapped because a lot of times we think of this as a page table, but again, there's been many ways that this has been done. We'll talk about a couple of them today. But the nice thing about this is that since you're always getting chunks of memory of a specific size, you can always pack those into physical memory. So that's really nice. You don't have any issues there. But you do have a little bit of internal fragmentation, because if a process needs 1 kilobyte, you give them 4. So that's a little bit of a waste. Most of the time, thankfully, it's not that big of a waste, because computer programs, typically, you'll lose a fraction of a page. You'll see this actually in the process.c code for the PINTOS process address space mapping stuff. You lose a little bit of a page per segment in your ELF file. So you might have 6 segments, something like that. So you might lose, on average, 3 pages worth, more or less, due to fragmentation issues. That's not a lot of memory. Okay. So yeah, this does motivate the choice of small page size. Now, there's other things that motivate this as well, like the fact that I/O is expensive. I don't want to move a giant amount of data back and forth, but I don't want to move 1 byte back and forth as well, because then I don't really amortize my cost of doing the I/O in the first place. So anyway, typically the page size will be on the order of kilobytes. Now this is wild. One way that systems have done this mapping is just having a set of registers that actually store the mapping directly. The PDP-11 was one of these systems where basically 64 kilobytes address space, pages were 8 kilobytes. There's not a lot of pages that you can fit in the PDP-11's address range. And so they would have 8 registers that just control the memory mapping. And if you wanted to change a part of the memory mapping, you could. Okay, so that's an example where the mapping was actually just stored in registers. Most of the time we do things in a page table. And of course you have an entry for every virtual page in the virtual address space. So if you have 4 gigabytes of virtual address space, you would have what I think it's 1 million entries in the page table, or whatever what is it? I can't even remember the binary. What is it? 2 to the 20 version of that. But this is fine. It works really well, except for the fact that you have to actually talk to this thing to figure out your address mapping, and that's in memory, so it's going to be slow. And so we have buffering or caching that we use to store lookups on the processor. And we presume we're going to run quite a few instructions from each process, so let's go ahead and cache the lookups in the processor to make that mapping fast. And so that's the thing that basically makes this virtual addressing. There was a time when people thought virtual addressing was just going to be prohibitively slow. Okay? Now it's just the way we all do it. So you can see that they've surmounted those issues. Okay? So we've talked a little bit about TLB misses in the past, so I'm not going to spend too much time on this, except for the fact that there's some processors that allow TLB misses to fire an interrupt. So imagine this. You perform a memory access. The page table mapping is not in the translation look-aside buffer, so what does it do? It fires a software interrupt so the operating system can resolve the TLB miss. Does PINTOS have TLBs? Well, it has, the processor has translation look-aside buffers. So basically, I believe that it emits the instructions to flush the TLB cache when it switches between user process address mappings, because the translation look-aside buffers become invalid. But yeah, it has them just by virtue of the fact that the processor supporting it does. And thankfully, you don't have to think about software interrupts when there's TLB misses, because IA32 doesn't do that. It tends to be on processors with much larger address spaces. Okay, so simple page table where we have 1 entry for virtual page. Of course, we talk about this in CS24, so I'm not going to spend too much time talking about it. This is prohibitive because the table becomes too large. If we had a single flat table, we're presuming that our entire address space is going to be mostly utilized. That's almost always not the case. So why have a dense representation for your page table when a sparse representation is going to be much more efficient? And so we call this hierarchical paging, where basically you take your virtual address, and remember the virtual page offset always comes across. That's the easy part. But the remaining address bits we divide into some number of levels, and each level corresponds to a page table. And so you can think of each one of these levels being, is represented by a node with a big fan out. So on IA32, I think it's 1K child nodes, if I remember correctly. And so same thing with x86-64. We have 4 levels, and each one has, I think, 512 children. So each node has 512 children. And so that's a much more efficient representation of a sparse address space because we only represent the parts that we need. If you have a chunk of memory that's unused, you just put a null in the entry for that page table level, and then the processor knows everything below that is not present. Okay, so that's the way that we go ahead and do that stuff. Makes it pretty simple. So IA32 has 2 of these levels. Let's see what else I say about this. You have the page directory, and then you have the page table. And so given that we have 20 bits left over from our virtual page offset is 12 bits, and we have 32 bits, so we have 20 more bits, and we just divide it in half, 10 bits per each level. So that's pretty easy. I don't know that you'll care about this too much in PNTOS because you have functions that take care of these mappings for you. What you will care about, and what I think some of you have already encountered, is that you'll get a physical page in the kernel with one address, and you'll have to write into that page, put stuff into it, and then you'll map it into the user address space at a different address because it'll be what the user process needs, and then the user process will see it at its own address. So those are some of the things you have to sort of go through the mental gymnastics of keeping track of the fact that a page may appear in multiple addresses, and since you're in the kernel, you'll be accessing it with one address. Okay, so x86-64 has a 48-bit address space, which is kind of weird, because it's like 64 is right in the name. Why doesn't it have a 64-bit address space? Because that's just not the way they design it. So 48 bits of address and 4 kilobytes of pages. So again, we have 12 bits for the offset, and so that leaves, what do we got left? 36 bits for the rest of it, and so it's divided into 4 levels, each one with 9 bits. And so the entries double in size, so that's nice because we need to specify a little bit more stuff, but we now have a deeper hierarchy. And the challenge is, as the address space keeps growing, you can see how this happens. Well, you need to have more levels to access. I think it was the Spark processor has a true 64-bit address space, and if they were to design it this way, they would need 7 levels. And so who wants to do 7 memory accesses just to see where your virtual address maps? And your translation look-aside buffers get really complicated and all of that kind of stuff. So when you start getting above a certain size for the address ranges, then there's some interesting techniques, like hashing instead of just having a tabular format or a tree structure that you navigate. Okay? So like it says here, you hash the virtual page number to find the physical page. And of course, that seems crazy to do in hardware. And so typically what is done is you have to have some way of resolving these issues. Because like I say here, we have 2 different kinds of hash tables. We could have open addressing where we just hunt for a slot. The hash just tells us where to start looking. Or we could actually have overflow buckets, which tends to be the way that these hash page tables work. Okay? This is where the processor will trigger a TLB miss to go into the operating system, and the OS will navigate this structure. That's the only way that you can really build this in a general purpose way. So all that really happens is the MMU will try to look in the translation look-aside buffer. It wants a TLB hit because then it can take care of everything for it. But if you have a TLB miss, then the OS is invoked, and the OS handles navigating this hashed page table. Some systems use clustered page tables, which is just a fancy way of saying that each overflow bucket can hold multiple addresses. That's like an obvious thing to do. Okay, so a clustered page table might have 16 of these virtual to physical page mappings in each little bin, and then we can just overflow chain those things together. Again, if you have this kind of clustering, then you want to have software invoked TLB resolution. TLB lookup resolution so that you can have the OS implement that complexity. But you can see that this is crazy. It's necessary because you have a large address space, but it's crazy because the processor is now running software to resolve memory accesses, so it's going to be slow on misses. Okay, crazy stuff. Last idea, the last crazy idea that we're going to talk about today, that again you see on very large systems. And again, I think the PowerPC processor is an example of something that does this, is an inverted page table. So typically we map virtual addresses to physical addresses because what do programs emit? They emit virtual addresses, and we have to map them to physical addresses. Well, if we have a really large address space and we don't want to have one virtual to physical mapping per process, let's invert it. And now we'll have one physical address mapping to virtual addresses. This is unusual. Okay. So I have one table now that maps physical pages to virtual pages. And so this is basically trying to reduce this memory overhead. So traditional page tables, each process has its own page table. With an inverted page table, the entire system has one inverted page table that is used for everybody. Okay, that's the idea, which is crazy. Okay. And of course we have a challenge because how do we actually use this for our address translation? Programs are emitting virtual addresses, and now I have an inverted page table that says how to go from physical to virtual, but that doesn't help me because I have a virtual address. Well, the inverted page table is typically indexed or accessed via hashing as well. Okay, so this is where the UltraSpark processor does its thing with its giant 64-bit address space, and PowerPC does a similar thing. Pretty crazy if you think about it. Okay, that we have all of this support just to deal with this issue of the memory overhead of this per process page table. Now again, this was back when memory was a lot more expensive and a lot smaller than it is now. Nowadays it's just like, okay, just throw more memory into the system. Who cares? But back then, this was there were pretty significant physical limitations of these systems we were running into. Now there's another interesting issue with inverted page tables. How do you provide shared memory? It's easy to do shared memory with normal paging because you have two processes that decide we want to share memory, and so they each have an entry in their little personal address spaces mapping to the same physical pages. No big deal. They may appear at different addresses in each one's address space. No big deal. They have to deal with that complexity. But the system, from the system's perspective, it's fine. Multiple processes are sharing a single physical page or maybe a handful of physical pages so they can communicate. That's like impossible to do with this approach because now I have each physical page mapped to the one process's virtual address space that's using it. So how do I actually provide shared memory? Well, there's two crazy approaches that have been used for these systems. If I have a single processor system, okay, why is it important that I have a single processor system? Well, because I have some fun shenanigans to get up to. Okay, remember, I have a single inverted page table. If I have a single processor system, how many processes are running at any given time? That's an easy question to answer, right? I have one process running it at any given time if I have a single processor. So if I have a single processor system running a single process, which process actually cares about the shared memory mapping? The one that's running, right? Any of the ones that aren't running and have access to the same shared memory, they don't care because they may be ready, they may be blocked, they may be doing something else, but they're not running. And so basically, what I can do is every time I switch to a process, I can look to see if it has any shared memory areas. And if it does, yeah, I update the inverted page table to point that process's virtual page. I should say I point that region of memory to that process's virtual pages. So you see there's a little fix-up we can do every time we switch back to a process. If it has shared memory, update the inverted page table to support that process at that time. And then when we switch away from it, we update that mapping to something else. So that's a pretty simple approach. That one's fun. There's another interesting approach, which you start seeing in, again, some of the more advanced processors that are for server systems and actually have this kind of situation arise a lot. It's kind of wild to me because one of my early programming jobs when I was here at Caltech as an undergrad was on Spark server systems that had pretty heavy shared memory usage, and it kind of blows my mind that this was all going on behind the scenes and I had no idea in the OS to support shared memory. Another option, though, is in the inverted page table. So I've got physical page numbers and I have virtual page numbers. I can add another column to that, which is a process ID. I can have some simple process ID that I add into that table. And now I just say the combination of process ID and physical page number have to be unique. And so I, obviously make my inverted page table a little bit more complex, but I have a way now of mapping the same physical page with multiple processes to different virtual addresses. So that's another technique that's been attempted. This one's pretty simple, though. I kind of like it. It has a certain elegance to it, I suppose. Anyway, any questions? So these are some of the more esoteric approaches that have been taken for process virtual memory. What we'll do next time is we'll pick up the more typical approaches and how we typically need to implement these things in operating systems. Hopefully it'll get you ready for the 5th project and get you underway. So, all right, we'll see you all next time.